Alright, we've just done a couple of experiments with an ordinary duty lead, and we've proven that the voltage drop is proportional to the length of the lead given the same current. You'll recall that we were losing roughly round about 1 volt per metre of lead with my jug plugged in, which is probably around 8 to 10 amps. So now let's go the other way and try and prove that the voltage drop is inversely proportional to the size of the cross-sectional area of the conductor. The one we had before was about 1.5 mil. I now have connected a 2.5 mil cable of 25 metre length. Now if we'd have had a 25 metre length of the 1.5 mil, we would have expected to get a voltage drop of around about 25 volts. So let's see what happens when we plug in a lead 25 metres long with 2.5 mil. Okay, there is the mains voltage with no load plugged directly into my outlet. There is the mains voltage with the jug turned on. So we've dropped about 10 volts, which is roughly what we expected to have. With the magic of editing, I have now moved the voltmeter to the end of the lead, and you can see it reads mains voltage, which is what you would expect because there's no current going through it. And I will turn the jug on, and you will see the voltage drops to 230, which is 10 volts less than we were getting on the mains voltage with the jug on. So that means we're losing roughly, give or take a bit, 10 volts through the 25 metre extension lead. Remember, we expected to get 25. So what that means is the larger the lead, the less resistance, therefore the less voltage drop, therefore the less power dissipated in the lead. Okay, so let's look at some simple sums. We know from Ohm's law that the resistance is equal to the voltage divided by the current. Okay, so we had 10 volts drop roughly through the 10 metre lead, and we had 8 amps going through it. So we want to calculate the resistance of the lead. So using our trusty old calculator, we have 10 volts divided by 8 ohms equals 1.25 ohms resistance in the lead. It equals 1.25 ohms. Now let's calculate the power lost in the lead. But to calculate the power, or the wattage, is equal to the voltage drop multiplied by the current, P equals EI. You can also calculate it by using P equals E squared over R or I squared R. But because we have the voltage and the current, we can just do a simple multiplication, which is equal to 10 volts multiplied by 8 amps equals 80 watts. So that's 80 watts dissipated in that small extension lead at a reasonable current of 8 amps. Which means if you coil that up in a tight coil, you will have the same heat dissipated in there as you would in an 80 watt globe. So obviously your lead is going to get hot. So that is the reason why you shouldn't have a lead curled up. So what can we conclude from all that? Firstly, the voltage drop Therefore the losses, therefore the heat in a lead is directly proportional to the length of the lead and inversely proportional to the thickness of the lead, the cross-sectional area of the conductors. You can see that is significantly larger. So if you're making up a lead or if you're replacing the lead, bear in mind how long it has to be. Don't make it any longer than it has to be, and don't make it any smaller than it has to be. These are fine for computers, printers, TVs, office equipment, stuff that doesn't draw a lot of current. But if you're going to be using it in your workshop or with kitchen appliances, heating appliances, which traditionally take more current, you're far better off to go up to the 2.5 mil. But whichever way you go, keep it as short as you possibly can, therefore you'll reduce your losses, therefore you will reduce the heat.